Good afternoon, gang. Sorry that I can't be with you today, but I'm here with you through the magic of YouTube. Wanted to talk a little bit about Graham's Law, which we just finished the hour with yesterday, and I think that you would benefit from having a couple of examples shown to you before I set you loose on some problems with it. This is one thing that we did yesterday, remembering the ideal gas law can have density in it. I know this problem set I'm about to give you has density in it. If you remember what we talked about yesterday with diffusion, diffusion is the spreading out of a gas. And that's what you see here when it starts. The animation's over now, but when it starts down in the corner, spreads out to fill out its entire volume that's available to it. That's what diffusion is, the spreading out of a gas. There's another term that's related to diffusion that I want you to also know. And I'm going to pause for a moment here and let you write it down. The word is diffusion. This probably was not seen in biology. Diffusion has to do with when you have a container of a gas and it has a hole in it, like this. The gas particles, the ones that would bounce where that hole is in the container, they would just escape out of the container through that hole. The rate of diffusion is described by Graham's law just like diffusion is. So take a moment, write down what the definition of diffusion is. The escape of a gas, the escape of gas particles through a tiny hole in its container. If you've ever had latex balloons that are filled with helium, they'll be up on the ceiling, and you go to bed that night with the balloons, and you don't have to go to bed with the balloons, but they're there up on the ceiling at nighttime. You wake up in the morning, and they have fallen to the ground. What's happening is the latex has little holes in it. It's not a totally sealed surface. And so the helium particles, because they're so small, will escape out of the pores, which really that's what that is a pore. And so that's why some of the helium escapes out of helium balloons, and they'll fall to the ground. Mylar balloons, those real shiny colored balloons, they don't have those little pores in them, so mylar balloons will stay up for a long, long time, weeks and months usually, where latex ones, the rubber balloons, they'll go flatter like overnight because of this process of diffusion. All right, moving on. You saw this yesterday. Now, thank you, Mr. JB.
That was for him.
Thank you. This is Graham's law of diffusion. I was using 1s and 2s when I showed you in class, but A's and B's are the same kind of thing. What I want you to notice is the comparison of the rates of diffusion, or diffusion, of two gases, with A being compared to B. Notice the big thing about this is the square root of molar mass of B on top over A. Whichever gas you choose to be on the top on this side, the other gas should be on top on the other side. And don't forget to use the square root of the molar masses like that. On the test, I am going to give you all of the gas law formulas, including this. Just knowing how to plug the numbers into this is the big thing. Well, what does Graham's law tell us? This is mathematically a relationship between two rates of gases, but what does it really mean? If A is faster, that means the numerator is bigger than the denominator. That means over here, if these two fractions are equal to each other, the numerator has to be bigger than the denominator here. Which means if A is faster, that means B must be heavier. And so we get this relationship is, the heavier the particles of a gas are, the slower that gas will diffuse, or diffuse. This is really important. If I have hydrogen that I have a hydrogen balloon that I pop, the hydrogen will diffuse through the room faster than any other gas will because hydrogen is the lightest gas. Something like radon, a very heavy gas, that will diffuse much more slowly because it's a heavy molecule, or in the case of radon, atom. So this is true, and this is like qualitatively what I want you to know about Graham's law. Heavier gases diffuse more slowly, and lighter particles diffuse faster. All right, we're going to do 2 examples, and then we're going to be done. So if I am on one side of a room, and I release a jar with ammonia and a jar with ethanol molecules in it, which one are you going to smell first? If you're sitting across the room, those particles are going to be diffusing. Which one are you going to smell first? Well, what it said on the previous slide was that the the lighter the gas is, the faster it will diffuse. Which of these two are lighter, is the lighter gas? Looking at the molar masses, this has a molar mass of 17, 14 and 3 ones, and this has a molar mass of 46. So this one, being the lighter gas, is going to be the one that diffuses across the room, and you'll be able to smell the ammonia across the room before you would smell the ethanol. That one didn't count as one of my examples. That was a qualitative example. I want to show you two ways that you use Graham's law in a formula. All right, take a look at this one. At a certain temperature and pressure, remember the temperature of the two gases always have to be the same for you to use Graham's law. So what the temperature is doesn't even matter. But they always have to be the same for both gases. So you have chlorine molecules have an average velocity. This would be the rate of chlorine of 324 meters per second. What is the average velocity of sulfur dioxide? So you know what both gases are. You've got chlorine, Cl2, and sulfur dioxide, which is SO2. Now Graham's law says this. It says that the rate of gas 1 over the rate of gas 2. Now I'm going to replace the 1s and 2s with what the actual gases are. So I'm going to say rate of Cl2 over the rate of SO2. So I'm just naming the gases here in Graham's law equation, equals the molar mass of SO2. Remember, whichever one was on the bottom on this side goes on the top on that side, over the molar mass of chlorine. Now what do we know in this problem? We know the rate of the Cl2. We're given that. It's 324. We know from the periodic table both of those molar masses. So the only thing you don't know is this. What's the problem asking for? What is the average velocity of sulfur dioxide under the same conditions? So that's what it's asking for. What is the rate of sulfur dioxide? So just solve for it. The rate of Cl2 is given to us, 324, over x equals square root of the molar mass of SO2. That's 64. Remember, our unit on molar mass is grams per mole. And this unit was meters per second. The molar mass of Cl2 is 71. And you're going to cross multiply and solve for the x. That's how we use Graham's law.
He learned that last year.
I did learn that.
He must have had a brilliant Chem 1 teacher. Go ahead and put the camera on that guy.
Look at this guy.
Borax. We have
Introduce yourself, please. Go ahead and stop it. Oh, no, don't stop it. Don't stop it. I can't.
Oh,
I'm
you're
filming
doing
something
a
for next,
thing.
yeah, for tomorrow.
I feel terrible.
Mr. JB then.
Mr. JB, guys.
There he is. Organic chemistry teacher.
How about borax? Do we have that? I know I've seen big.
I know we have borax. Sodium borate. I think the far right cabinet has sodium
I
borate
thought
in it.
so. What about the 30%?
I know I have borax though, so give me just a couple minutes later when I'll be done.
And what about the hydrogen peroxide, 30%?
Yeah, we have it. Yep, I used it last week.
Where's that at?
It's in the far right cabinet over there in the peroxides.
Okay.
You'll see.
Forgive me, I didn't know you did.
No problem, that's all right. So anyway, cross multiply sulfur x, and just don't keep track of the square roots. 324 times the square root of 71 equals x times the square root of 64, and then solve for x. It's not that hard. Okay, so you're going to get x equals 340. That's how we use Graham's law. One more example, if we can go back over here. Sometimes you're not going to be asked for a specific component of Graham's law, but rather a ratio. What is the ratio of hydrogen's diffusion to nitrogen's rate of diffusion? So what we're looking for here is, the question is, what is the ratio of the rate of hydrogen diffusing to the rate of nitrogen diffusing? Remember, both of those are diatomic. You don't have to find one or the other, you just want to find that ratio. So that means, what's it going to look like? Square root of the molar mass, whichever one was on top here does not go on top on the other side. So it's going to be the molar mass of nitrogen over here over square root of the molar mass of hydrogen. Okay, so anyway, we just want that ratio. You're solving for that thing right there, and that's what the question is asking for. So we can do that. Molar mass of nitrogen is 28, square root of it. Molar mass of hydrogen is 2, and square root of 28 divided by the square root of 2, whatever you get, and go back to the board. What I'm really asking for there is what is the ratio of the rates? How much faster does hydrogen diffuse than nitrogen? And that would be when you take the square root of 28 over the square root of 2, you're going to get a ratio of 3.74 to 1. So that means that hydrogen will diffuse across the room 3.74 times faster than nitrogen does at the same temperature. I want to thank Mr. Spencer Eaton, Jr. for helping me record this today. I hope that made sense to you and you'll be able to do some of the problems that I give you Friday afternoon. Have a good weekend.